Okay. Good. Yeah. There is just a second. Some screen. Great. Yeah. I think it is now recording. Yeah. So omega is a probability space, omega AP, and X, capital X is a function from omega into the real line. As you all know that for any subset in B, the real line, see X inverse B is the inverse image of that set, and that is all little omega in capital Omega, such that X omega is a point in B. So we say X is a real valued random variable if X inverse of the interval minus infinity to X is an element of that sigma algebra skip-T. So that it makes sense to talk about probability of this X inverse of minus infinity to X. So if this happens for every X in R, that is called a real valued random variable. Again, this kind of thing you would have seen in your earlier class. And if in addition, the range of F, range of X, see, range of X is going to be a subset here. If that happens to be a finite or a countably infinite set, this is called a discrete random variable. In general, this denumerable set will be a kind of discrete set, in the sense there will be enough distance between any 2 points. So it is called a discrete random variable. Okay, note it down if you want to. So if it is a real valued random variable,
sir,
yeah.
Can you just once again go to the okay? Yes, sir. Yes, sir.
Sure.
Okay, sir. Fine.
Yeah.
Fine.
So let X be a real valued random variable. Then one can show that X inverse of any open interval is also an element of that script A. X inverse of this open at one end and closed at other end, that is also in A. And that infinite open interval is also in A. And X inverse of any singleton point is also in A. So that it makes sense to talk about probability that X is taking value between A and B, or probability that X is strictly greater than A, and so on. Or since we are going to deal with the discrete random variables, probability let the random variable takes the value A. All these things make sense. So as an abbreviation for notation, we will generally write probability X less than or equal to little x for denoting probability of X inverse of the interval minus infinity to X closed at X. And similarly, probability X, capital X equal to small x would be the probability of X inverse of the singleton X. And similarly, these things. So that all these objects are meaningful because the corresponding X inverse is an element of that collection script A. And since probability that P is a function defined on this as its domain, all these things make sense. Okay, note it down if you want. Okay. So let X be a discrete random variable now. So let us denote by the range of X by capital B. So that consists of points X1, X2, etc. So it's clear from since B is the range of X, X inverse of B, probability of that is equal to 1. Probability of that set. This set is an element in script omega, script A, and that probability is. So also probability of X equal to little xi, where xi is some point in B, that is this object, that we have this notation for. Okay, sorry. All right. Many of these things you already are reasonably familiar with. So let B be the range of X. It's a finite or enumerable set. So now we are going to define a function F. Again, you have seen this function, the distribution function of X. And usually the notation for distribution function is capital F and things like that. Capital F of X is probability that X, capital X is less than or equal to little x. That means it is the probability of this set, the set of all omega in capital Omega, such that X omega is less than or equal to X. That I think there should have been a braces here missing. Anyway. So that capital F is called the distribution function of X. Okay, note it down if you want to. There is one more function which we shall introduce now. So define the function little f on the real line by little f at X is probability X equal to little x. It is this. This function is called probability mass function. Some books also called discrete density function of the discrete random variable capital X. Now it is clear that if this point little x is not an element of the range B, then this little fx is equal to 0. And we will generally assume that probability of capital X equal to little x is strictly positive for all x in B. If for some x in B this happens to be 0, one can even eliminate that point from B. That's the point.
So sir, I have a question. So if x not in range of capital X, then f of x will be 0, right?
Yeah, little f of x will be
0. Little f of x will be 0, yeah. If x is not in range of x, yeah.
So we will generally assume this will be a, consequently it is the case that little f of x is strictly positive if and only if x is in B, in the range. Again, note it down if you want. Now, certain properties of these things. Now, note that capital F of x, that is the probability x takes the value less than or equal to little x. And since the random variable X takes the values are taken in B, only those B, those Y which are in B and also Y less than or equal to X will be included in the counting of this probability. That is it. This. So it is basically summation over Fy, all Y such that Y is in B and Y strictly less than or equal to X. And this whole object, this summation, is dominated by probability X belongs to B, and which is 1. So therefore, these equalities are clear. So this concerns the probability of an event. Therefore, it is greater than or equal to 0. And this quantity is less than or equal to 1. You would have also seen in your earlier class that the distribution function takes values between 1 and 0. And because of these things, the following facts are fairly obvious. If you have 2 points X, Z, which are successive elements of B, that is strictly between X and Z, there are no other element of B. In that case, the Fy remains a constant between X, that is on the interval closed at X, open at Z. At Z, it may have a jump.
No, but I have a question.
Yeah.
So we know that the range of F is a countable set.
Yeah.
But the property you mentioned, this need not be true for any countable set. Means there are countable sets for which between 2 successive elements there cannot. Means
no. Generally, this is assumed that it is a kind of discrete set, like 0, 1, 2, etc. We may sort of exclude from our consideration things like rational numbers. Okay?
Yeah, exactly. Yeah.
Yeah. Okay.
So basically, rationals and other stuffs we do not consider.
Or we'll say because they don't arise so much in practice. Okay, it may be a subset of rationals like dyadic, not dyadics. Something which there is a between any two there is a strictly some minimal distance is there. Okay, minimal distance.
So we can take the set of integers or set of naturals.
Set of integers or even set of, let us say, things multiples of half.
Multiples of half. Okay. Yeah.
It's like that. Okay. All right. It is not coming. I got it.
But sir, why are you writing that Fy equal to Fx for all Y? Because you are saying that there are 2 successive elements of B. So
yeah, but this is an increasing function, no? See here. See F of, let us say X is a point in B. Then that point will be included in this count.
Yeah.
Now you go to a Y which is bigger than X but strictly less than Z.
Yeah, but such an Y cannot exist because you are saying that X and Z is yet to.
No. This capital F of this thing is defined for every X.
Yeah, it is defined for every X. Yeah.
So this function capital F will remain a constant in this interval. In this closed at X, open at Z. So, for example, you take, since you are already seen a course in probabilities.
Yeah, I got your point. So I got your point. Yeah. So it will remain constant and closed X, open Z.
Yes, because at this point it will have a jump. It can have a jump.
Yeah, it can have a jump. Yeah, depending on the probability value at Z.
Right.
Yeah. I got your point, sir.
So that is the next thing. So therefore, the distribution function capital F is continuous everywhere except at the points of B, where it will have a discontinuity. And if X is a point in B, then little f at X is f at X minus f at X minus. So fx minus is the left limit at x of f at x. That is capital F of y, limit of capital F of y as y increases to x. That is, y is coming from the left side. Again, this you have seen in your earlier course. So at the point z in this case, the possible jump at z will precisely be little f at z. That is the probability that the random variable x takes the value z. So at points in the range B, that capital F will have a jump, and the magnitude of the jump is precisely little f at x. Note it down if you want.
So basically, it is a kind of step function, we can say.
Yes, it is. Step function in increasing, non-decreasing.
Yeah. Non-decreasing step function, capital F.
Yeah. Moreover, f is right continuous everywhere. That is, if you come from the right, then the limit fx plus, that is limit of fy as y decreases to x, is same thing as fx. So capital F is a right continuous function having discontinuities only at countably many points, possibly countably many points. Okay. Yeah. So if A is less than or equal to B, FB minus FA is this object, and this is not greater than or equal to 0 since it is probability of some event. So it is a non-decreasing function. So the distribution function is a non-decreasing function and right continuous, having countably many, at most countable number of discontinuities, and takes value between 0 and 1. Something more also we can say. F at minus infinity, which is by definition is the limit of fx as x goes to minus infinity, that is 0, and limit at plus infinity, that is limit f of x as x increases to infinity, is equal to 1. So from what all we have given in the previous, these two slides, that is in this as well as the next one, you can see that if you know capital F, from that you can find out little f, and if you know little f, from that you can find capital F. So from the distribution function, you can get hold of the probability mass function and vice versa. Again, something which you know. Okay, so this is another assumption we will generally make. We will assume that to describe a discrete random variable, it is enough to specify its probability mass function. In other words, in many instances, we may not bother to describe the basic probability space. Of course, since we may be dealing with the discrete random variables, it is not a big issue. You will that it's this kind of thing is assumed even for continuous random variables. So those kind of intricacies, those of you who do measure theoretic probability will perhaps understand better, but we will assume this. In some cases where we can describe some kind of an experiment which is describable, then that can be done. You can even sort of explain this. But this will be we will, in other words, we will assume that the random variable is given to us, given once we have its probability mass function. Okay. So let us quickly look at what is an expectation of X. So the standard, this thing, discrete random variable X, probability mass function little f, and V is the range. So if summation over X varying over this range B of mod little fx, mod little x fx. So that is same thing as if you denote these, since these are these elements of B are denoted x1, x2, etc. Summation over xi, mod xi fxi. So this is a countable sum. So it is if this converges, then one says the random variable x has finite expectation or equivalently finite mean. And in that case, the expectation of x is defined to be this thing without that mod here. If expectation x exists, then it's a real number. All these things you know already. Okay. Yeah, small proposition. Again, you would have seen its proof even. We will just go through it proof also soon. Let x be a discrete random variable with probability mass function f sub capital X. Because in this thing, we will be dealing with more than one random variable, it is better to denote the dependence that f depends on the random variable. Little f depends on the random variable. Again, this kind of a notation will be familiar to you. So let little b be a function, real valued function on the real line. So then it makes sense to talk about V composition X. So that is V of capital X, we denote by capital Y. It is clear that Y is a random variable, and also Y is actually a discrete random variable, because the range of Y will even be smaller than, I mean, it can be a subset of this. Not subset, the image under V of a countable number of points at most. It's not a subset, sorry, that's an incorrect statement. It will be a subset of range of, range of this thing, under V, range of V, under V. We will soon describe that. Then this result says this discrete random variable Y has finite expectation if and only if the summation over xi varying over B, mod Vxi, f sub x xi is finite. And in such a case, the expectation of Y is given by this expression without the mod. That is summation over xi, Vxi, f sub x xi.
I think this result is pretty obvious from the.
Yes, but just let me just, that is since it is very obvious, we will go through the proof. If it's not obvious, we will assume without proof. I mean, just since we are going to the rapid review, it is just to sort of warm us up. Yeah, it is pretty obvious. The only point.
Do you mind going to the previous slide?
You want me to go to the previous slide?
Yeah, thanks.
Is it okay? Shall I go to the next one?
So yeah, so we're defining expectation with respect to the given probability mass function, right? And Not from the measure defined on the
No.
workspace.
See, once that mass function is known, effectively we know that measure. Okay.
Yeah, that was the assumption that you talked about at the end of the previous slide.
See, the thing is, once we have the probability mass function, this
Right.
omega AP we will forget.
Right.
How exactly that random variable we got hold of, we need not really know.
Right.
Okay, because all the probabilistic information which we are going to infer is contained in probability mass function.
Right. So if you go to the next slide again, then this only allows me to define expectation of X given a probability mass function F on X, right? It doesn't let me define it for another variable Y if I don't have F of Y.
Yeah, so precisely that is what we have to prove.
Right. Okay. Yeah, thanks.
Yeah. See, as he has pointed out, our friend, see, the point in the proof is that the expectation of a random variable, let us say Z, let us capitalize Z, is in terms of the probability mass function of Z. So now, in case Y happens to be a function of X, we are relating expectation of Y in terms of the probability mass function of X. So the idea of proving this, basically, how to relate the expectation of Y, which will generally be in terms of little f at sub Y, and this object. Okay? Yeah, it's good that you raised this question. Okay, so we will look at the proof. We will prove only the first part, that is this part, and the other thing is just by definition of expectation. So, as we had noted earlier, Y is a discrete random variable. And the range of Y, let us denote by Y1, Y2, etc. So we will denote by A, capital A sub J, all those points Xi in the range of X, that is B, such that V of Xi is equal to Yj. In other words, this Aj is nothing but V inverse of the point Yj, its intersection with B. See, V is a function from real line to real line. So if you are given a point Yj in the real line, its inverse image can have points from B, or also may have points which are not in B. Consequently, the set Y inverse of Yj, the singleton Yj, which of course in our not kind of a notation, capital Y equal to Yj, is precisely the set X belongs to Aj, so it is X inverse of Aj. Aj, remember that it is a subset of the real line. It's a subset of the real line, it will be a subset of B. So let little f sub Y denote the probability mass function of Y. And the probability mass function of Y, we need to bother what are the values at only points in this range of, this thing, what is it, B inverse of this set B. So from what we have noted here, f sub Y at the point yj is nothing but probability the random variable y takes the value little yj, which from what we have got here is the probability that x takes the value in aj, and this aj is the at most countable set, and the elements of this aj are points in B as well as V inverse of yj, and that is f sub x at xi varying over aj. And this will be a finite number, it will be less than or equal to 1. So the range of capital Y is denoted by y1, y2, etc. So union over J of AJ is B, and also these AJs are disjoint. So that is two different Js, the AJ would be disjoint. Consequently, we have summation over Yj mod Yj f sub y at Yj, and that is equal to, we now expand out this in using this. That is this one. We are using this expression here. So summation over Yj mod Yj, and then summation over xi varying over aj f sub x at xi. And this is equal to that. Now write that for every the fixed j, the yj is precisely v at xi for some xi in aj. It is this object. Summation over yj, the next summation for fixed j, xi varying over aj mod vxi f sub x, and which precisely is this. So this is finite. Therefore, expectation of expectation of y exists. And expectation of y in terms of this is precisely this without the mod here. And therefore, the second assertion is also clear. So the proof is quite simple. It is just that since the expectation of a random variable is given in terms of its probability mass function, and when that random variable happens to be a function of another random variable, how to relate it to it? Note it down if you want to. Okay, I'll go to the next slide. So, because of what we have done in this small result, that enables us to define what may be called moments of x. Or rather, one can define expectation of this for any function of x. So in particular, we take some functions like x squared, x cubed, x to the power k, and things like that. All these things are of the form V composition x. Yeah. So that same notation as before, x is a discrete random variable, its probability mass function is little f, and b is the range of x. Let a be a fixed real number and k be a positive integer fixed. We say that x has a finite moment of order k about a if this happens. That is the expectation of mod x minus a to the power k is finite. This again, such a definition you would have come across earlier courses. So in that case, expectation of x minus a to the power k is called the kth moment of x about a. So if that little a happens to be expectation of x, then such a moment, kth moment, is called kth central moment. So you know that the expectation or the mean is a kind of centering parameter for the random variable. Those of you who have, in your statistics things, such terminology, you would have sort of seen its relevance or importance as a centering. That is, the random variable sort of takes value about its mean. And if k equal to 2, the second central moment, when it exists, is called the variance of x. And variance of x is precisely expectation of x minus ex whole square. Expectation of the square. And the positive square root of variance is called standard deviation. Again, these things you would have seen. And probably in your earlier course, the variance, etc., would have been set directly defined in terms of such an object.
So basically, when you are taking the kth central moment, no, not the kth central moment, so we are taking the kth moment of x about a, we are computing this expectation. So in our previous argument, the function v would be x minus a whole to the power k, the small v.
Small v is that power, yeah, x minus a to the power k. Correct.
X minus whole to the power k. Okay. Is it right?
Yeah, correct. Okay. It's all done. And though we will not be seeing moment generating function much in this course, it is just what is called moment generating function is also something like this. We define m sub x t as expectation of e to the power tx, which is, since these are discrete random variable, it is summation over xi, e t xi f xi, where xi varies over the range of x. So this is defined whenever this object is finite. So this whole thing is non-negative for every xi, and this function t going to mxt is called the moment generating function of x. And the domain of this function is all t in the real line, such that this summation is finite. In many contexts, from the moment generating function, we can gather a lot of information about the random. Though in this course, we may not have much occasion. It's an important object. I just have mentioned it in passing.
So does the moment generating function have any connection with the central moments, kth central moments for
under certain conditions? Under certain conditions.
Okay. Means basically when we take the derivatives of the moment generating function
under certain conditions. So let us not go into that, since we may not be using it much. Okay, we will keep our focus. I'm not trying to discourage you. You can refer to some books. Okay, so some examples of discrete distribution. So since we have mentioned that if the probability mass function is defined, the we will assume that everything about the random variable regarding the probabilistic information can be known. We will be satisfied with, let us say, describing just the probability mass function of this. In some cases, of course, very easily that can be visualized. So let B be a finite set consisting of exactly capital N elements. X1, X2, X sub n. So let X be a random variable such that probability of capital X equal to little x, xk is 1 over n for all the points in B, script B. So this random variable X takes value among the elements of B with equal probability and doesn't take value anywhere else. So in this case, the probability mass function of X is little f x is 1 over capital N for all the points in B, that is the finitely many points, x1, x2, x7, and it is 0 elsewhere. So we say that the random variable X has a discrete uniform distribution on the set, on the finite set B. Something like a random variable takes only values 0 and 1 with equal probability. Probability x equal to 0 is half, probability x equal to 1 is half. Like that. Okay. Next, binomial distribution. This again, we have seen it occur in a context. So therefore, we refer to that. So consider n independent trials of a success failure experiment with the probability of success in any trial equal to P. So let S sub n denote the number of successes in the n Bernoulli trials. So clearly, this S sub n is a discrete random variable taking values in 0, 1, 2, up to n. So from the previous set of things, that is notes, which or rather which has been put on Moodle, probability Sn is equal to k is n choose k, p to the power k times 1 minus p to the power n minus k. We have seen that for k varying from, k varying over 0, 1, 2, up to n. So the probability mass function of Sn is given by f of little x equal to n choose x, p to the power x, 1 minus p to the power n minus x, when little x varies over 0, 1, 2, up to n. And it is 0 everywhere else. This probability mass function is called the binomial density with parameters n and p. In such a case, we also say that the random variable Sn has a binomial distribution with parameters n and p. The n and p act as parameters n and p. Okay. The geometric distribution.
So can you just go to the previous slide? Just yes, it's fine. Okay. Okay.
The geometric distribution. Let P be a number between 0 and 1, strictly between 0 and 1. Let f, little f be given by f of x equal to p times 1 minus p to the power x. When x is varying over 0, 1, 2, etc. All those non-negative integers. And it's 0 everywhere else. You can easily see that f of x is strictly greater than or equal to 0 for every x. And fx is different from 0 only when x is varying over non-negative integers, 0, 1, 2, etc. Which is a countable set, enumerable set. You can also verify easily that summation k going from 0 to infinity of fk is equal to 1. It's your geometric series, using geometric series. So a discrete random variable little f with this discrete random variable x with this little f as its probability mass function, we say it has a geometric distribution with parameter p. You will soon see the geometric distribution in the context of success failure experiment. Note it down if you want. Okay. The Poisson distribution. Let lambda be a strictly positive number, and let f be given by, little f be given by, f of x is equal to e to the power minus lambda times lambda to the power x and divided by x factorial, as little x varies over non-negative integers. So clearly, this f is greater or equal to 0 for all x, and f of x is different from 0 only when x is a member of, x is a non-negative integer. And also it's clear that summation over fk, k going from 0 to infinity is 1. A discrete random variable with little f as its probability mass function, we say has a Poisson distribution with parameter lambda. You would have seen in your earlier course, this arises as an approximation when in the binomial case, when n times Pn stabilizes to some limit lambda. However, Poisson distribution's importance one can appreciate more when one does Poisson process in the continuing course, stochastic process too. It is, in some sense, it is also a distribution preferred by nature. It is the time. Oh, it is almost a time. So, okay, I will just start with the two-dimensional discrete random variables and stop. Yeah, function, let us say x comma y, we denote by x comma y. from omega to R2 is called an R2 valued random variable if for each point xy in R2, the set of all omega such that x of omega is less than or equal to little x and y of omega is little or less than or equal to little y is in script A. I mean, this particular set I have just described it as it is all omega such that this under the map xy at omega goes to this kind of infinite rectangle. Minus infinity to x, product minus infinity to y. That is in script. So if that happens, then this function xy is called an R2 valued random. In addition, if the range of this x comma y is a finite or a denumerable subset of R2, so that is the range will be points of the form x1, y1, comma x2, y2, etc. See, for example, these 2 points will be distinct if at least one of these points are different. X1 may be equal to x2, but y1 need not be equal to f2, yeah, y2, then these are 2 distinct points. For example, the point 0, 1 and 0, 2 may be in the range. So if that happens, x comma y is called a two-dimensional discrete random. So the notation for this is, say here when we have this, we can consider x omega here that denotes the projection of this xy omega onto the x-axis. And similarly, the other one. Note that for any little omega in capital omega, this is a point in R2, namely that is a vector. So that vector's x coordinate and y coordinate we denote by respectively by x omega and y omega. And this is one convention we generally make for various things. A vector valued random variable. So this x comma y is a vector valued random variable. The vector will be usually considered as the column vector. Though for typographical or for writing convenience, we write x, this y omega like that, or sometimes even x omega, y omega. It is to be understood as its transpose. That is, it is x omega and below that write y omega.
Sir, I have a question. So if x comma y is a R2 valued is an R2 valued discrete random variable, then can we say that the projections of x comma y, that is x omega and y omega, they will be one-dimensional discrete random variable?
That's an exercise for you. Yes, you can say that.
Okay, and also a sort of converse holds means.
Yes.
Okay, so
that will be
one-dimensional, then x comma two-dimensional.
I have asked that question. I can, I mean, without feeling any, guilty conscience, I can sort of go to the next slide. If xy is a two-dimensional random variable, then these guys x and y are one-dimensional discrete random variables. And conversely, as he had pointed out.
Okay. Okay, sir. Okay, sir. Okay, sir.
So let me finish that particular slide since you have made the thing easier for me. So conversely, also this is true. And let us say we denote by pi1 and pi2, respectively, the projection maps. So this pi1 is a map from R2 to R, the first coordinate projection, and similarly the second coordinate projection. So you can note that range of x will be the projection under pi1 of range of xy. And similarly, range of y will be the second coordinate projection of the set range of xy. And you can easily check that the range of xy, this two-dimensional map, it is contained in the Cartesian product of range of x and range of y. But this may not be, this can be a strict inequality. This may not be equal. So I leave it to you to find an example to show that equality need not hold. That is, find an example where range of xy is strictly a subset of range of x product range of y. Very simple examples you can consider. Since we don't have to sort of manufacture omega, AP and all that for now considering this kind of random variables, you just take some appropriate these things in the R2 and R and sort of find that probability function where it can take values. Just play around with random variables which takes the values just 0 and 1. So I will stop here for the day. It is almost 1 hour. So if there are no further questions or you wrote down any this thing concerning the slides, I will stop sharing and also end the session. For those of you who have next class, will be getting delayed. Okay.
We can simply take both x and y to binomial distribution with parameter.
No, don't go for such complicated things. Just I'm saying, just play around with the 0 and 1. Why do you want to make things complicated? Okay. Okay, I leave it to you.
Yeah, means we can do it for 0 and 1, but in that case, we can set the parameter of the binomial distribution n to be 1. So in that case.
Anyway, please. This is an exercise. I don't want to spoil your fun. Solve the exercise. Okay. Thanks a lot for everyone, and we will meet on Wednesday.